NASA brought back 842 pounds of moon rock to settle where the moon came from. Instead, those rocks made the leading story harder to explain. If another planet called Theia supplied much of the material for the moon, that planet should have left a chemical fingerprint. It barely did. We have pieces of the moon sitting in laboratories on Earth, and they still refuse to tell us exactly who their parent was. That is what makes the moon so strange. It looks like the most familiar object in the sky. You can see it from a driveway in Ohio, over a fishing dock in Florida, or through the windshield on a late drive across Arizona. It raises the ocean along the Atlantic coast and helps create enormous tides farther north. It even shows up in planting calendars that still tell people when to put seeds in the ground. The moon feels ordinary because it has always been there. Its birth was probably anything but ordinary. About 4.5 billion years ago, the young solar system was crowded with unfinished worlds. Their paths shifted under one another. Some passed close enough to disturb their neighbors, while others collided. The young Earth was still growing. There were no familiar oceans or continents yet. A large enough impact could melt enormous parts of the surface and change the entire planet before the planet had finished becoming itself. One of those lost worlds was later named Theia, after the Greek Titan who was the mother of Selene, the moon goddess. In the myth, Theia gives birth to the moon. In modern planetary science, a world carrying her name may have done something remarkably similar, only with molten rock instead of mythology. Nobody has a photograph of Theia. Nobody has a labeled chunk of it sitting in a museum. The impact site did not survive as a neat crater that you could circle on a map. The collision may have involved so much of the young Earth that asking for the crater is like asking which dent on a crushed pickup truck marks the exact moment it went through a wall. And the missing planet may not be completely missing. Some researchers think part of Theia could still be buried almost 3,000 miles beneath the surface, deep under Africa and the Pacific Ocean. In the classic version of the story, Theia was roughly the size of Mars and carried about 1/10 the mass of the Earth. It did not slam straight into the center. A direct hit would have driven too much material inward. A glancing pass would have let Theia escape after tearing off some debris. The useful collision sits between those extremes. It is violent enough to tear apart the outer layers of both worlds while still throwing a large amount of rock into orbit. The metallic cores would have plunged inward. The rocky mantles would have melted, and part of that material would have become vapor. Around the damaged Earth, incandescent chunks and droplets of magma began circling inside a vast cloud of hot silicate material. The moon would have grown from that mess. The asteroid impact linked to the end of the dinosaurs feels enormous because we know what it did to life. Next to the Theia collision, it would have looked more like a firecracker at a county fair. The comparison is only about scale. A planetary collision does not work like a military explosion. The important part is that the young Earth was not merely shaken. Much of its outer body was melted, mixed with another world, and reorganized. Before that idea became dominant, astronomers had other suspects. George Darwin imagined that a rapidly spinning Earth had thrown off part of its mantle. Edouard Roche supported versions in which the Earth and Moon formed together. Harold Urey and Horst Gerstenkorn studied the possibility that the Moon formed elsewhere and was later captured. There is no reason to spend a tour through the whole cemetery. The first idea gave the Moon the right kind of material, but required an Earth spinning almost hard enough to tear itself apart. The second made the two worlds relatives, but did not explain why the Earth ended up with so much more metal in its center. Capture gave the Moon an independent birthplace, but a body that large does not simply pull into the driveway and stop. It has to lose an enormous amount of energy. During the 1970s, William Hartman and Donald Davis, and separately Alfred Cameron and William Ward, turned the giant collision into a serious physical model. A major impact could put rocky material into orbit. Most of the iron could remain inside the Earth. Extreme heating could remove some volatile material, and an angled collision could supply the motion of the Earth-Moon system. For a while, the story looked unusually tidy. Then Apollo brought home the evidence. The astronauts did not only bring back rocks, they brought the moon into the cabin with them. Lunar dust clung to spacesuits and worked into seals. It blackened hands and floated in the air after moonwalks. During Apollo 16, Charlie Duke told Houston that the dust had a very strong gunpowder smell. On Apollo 17, Gene Cernan compared the cabin atmosphere to the smell after a rifle had been fired. The dust was not burning. Its surfaces had been blasted for ages by radiation and tiny impacts, and contact with oxygen inside the cabin may have created the smell. For the first time, the moon was not just something people could see, it had a smell. If you like science stories where a handful of dust can make a planetary explanation wobble, subscribe. This channel follows the evidence even when the clean answer starts getting messy. NASA also made a decision that looked almost absurdly patient. Some Apollo material was sealed and deliberately left untouched. The agency assumed that scientists decades later would have tools that the Apollo generation did not. In 2022, researchers at Johnson Space Center in Houston opened a deep sample tube collected by Apollo 17 and kept closed for almost half a century. Think about that for a second. The evidence sat in a container in Texas while computers shrank from room-sized machines to devices that fit in a pocket. The moon did not change inside the tube. Our ability to question it did. The rocks had already confirmed that the young moon was once largely molten. As it cooled, denser minerals sank. Lighter crystals floated upward and helped build the bright crust. The dark patches visible from Earth came later, when basaltic lava filled enormous impact basins. We still call them seas even though no waves ever moved across them. A good name can survive being wrong for centuries. The small metallic core of the moon also fits the impact story. If the moon formed mostly from rocky mantle material, while much of the iron stayed inside the Earth, the result should be a satellite with a relatively small core. Arthur Briot and his colleagues used lunar rotation, gravity, and old seismic records to sharpen that picture. Their work supports a liquid outer core surrounding a solid inner core, only a few hundred miles across. That little core creates another problem. The moon has no global magnetic field today. Apollo rocks, however, carry ancient magnetization. Some of them cooled when the moon apparently had a much stronger magnetic field. A planet or moon can make that kind of field when electrically conducting liquid moves inside a metallic core, roughly like a generator buried inside the body. The puzzle is the size. The lunar core is small. Keeping a strong internal magnetic engine running for a long time is difficult. Sonia Tiku and Alexander Evans have explored ways the lunar dynamo may have turned on in episodes, possibly when changes in the mantle allowed more heat to escape from the core. The white spot remains. A small metal heart once powered something that the present moon no longer has. Then came the isotopes. An isotope is simply a slightly different version of the same chemical element. For this story, the details of the atomic nucleus are less important than what isotopes can reveal. Different worlds develop slightly different mixtures. Mars has a chemical accent. Asteroids have theirs. The Earth has one too. The moon sounds almost exactly like the Earth. Measurements of oxygen, titanium, chromium, tungsten, and other elements show that lunar rocks are remarkably close to the Earth mantle. There are differences, but they are much smaller than the early impact simulations expected. The classic model gave a large share of the future moon to Theia. A separate planet should have left a clearer voice in the final mixture. Now the problem can be put on a kitchen table. The moon needs to have little iron. Its rocks need to look almost terrestrial. The Earth-Moon system has to end up with the right amount of motion, and the ages written into lunar minerals have to make sense. Fix one, and another starts complaining. One escape route is simple. Maybe Theia already looked a lot like the Earth. Work by Timo Hopp, Thorsten Klein, and their colleagues points toward Theia forming in the inner solar system, possibly even a little closer to the Sun than the young Earth. That makes the chemical resemblance less surprising. Less surprising is not the same as identical. Two houses can be built with bricks from the same factory. The dust behind the refrigerator will still not match perfectly. Robin Knoop changed the size of the collision. In some of her models, Theia is no longer a much smaller body hitting an almost finished Earth. The two colliding worlds are closer in mass. Their rocky layers mix more deeply, and the new Earth and the Moon can inherit similar material. Chemistry likes that answer. Motion does not. The collision can leave the system spinning too hard. Somehow, part of that excess motion has to be handed away later. Mattia Zuk and Sarah Stewart attacked that problem from another side. They started with a young Earth already spinning extremely fast. The impact could then throw a large amount of Earth material into orbit, helping the Moon inherit the same chemical accent. Later, a special gravitational relationship with the Sun could drain away some of the excess spin. In plain English, the system comes out of the collision with too much motion and has to find somewhere to dump it. The mathematics allows that. The problem is getting the Earth, the Moon, and the Sun through the right sequence without breaking something else. Computer simulations make this look less like a single theory and more like a planetary crash lab. Theia hits too directly. It dives inward. Theia misses by a little. It escapes. Change the speed. The debris falls back. Two moons appear. Then none. One moon has the right mass but too much iron. Another has the right material and the wrong orbit. Nature only had to run the collision once. Computers have to run it again and again because the original security camera melted with the building. Sarah Stewart and Simon Locke pushed the violence even further. Their work suggests that after some impacts, there may not have been a normal Earth at all. The planet could briefly become a synestia, a huge spinning structure made of molten rock and rock vapor that spreads far beyond the present size of the Earth. There is no normal ground to stand on. At several thousand degrees, material that would later become mountains behaves more like weather. If you have ever complained about a heat wave in Phoenix, this is where the comparison stops being useful. The moon can condense inside that structure. The Earth and Theia are already so mixed that asking which planet supplied each outer layer starts to lose meaning. The missing chemical fingerprint of Theia becomes easier to understand because the two worlds stopped being chemically separate before the moon finished forming. That solution runs into water. Apollo samples were once used to support the picture of a bone-dry moon. Better instruments changed that. In 2008, Alberto Sol, Eric Horry, and their team found water and other volatile material inside tiny volcanic glass beads from Apollo 15 and Apollo 17. Later observations found water-related signals at the surface. Then, a NASA mission called L-Cross slammed a spent rocket stage into Cabeus crater near the lunar south pole. The impact threw material into sunlight, and instruments detected water vapor and grains of ice. Picture a crater floor that sunlight may not have touched for billions of years. It sits on the same moon you can see from your backyard, but the bottom has been trapped in darkness colder than almost anything on Earth. Ice can remain hidden there like food forgotten at the back of a freezer. Except the freezer has been running since before the first animal existed. Where did the water come from? Comets and small asteroids may have delivered some of it. The solar wind can also help create water molecules in lunar soil. In 2025, NASA laboratory work strengthened that possibility by recreating lunar surface conditions and showing that particles from the sun can contribute to water formation. For future crews, polar ice is practical. It could become drinking water. It can be split to make oxygen. Its hydrogen could also become part of a fuel system, along with other uses around a future lunar base. For the birth story, the ice is more annoying. A collision hot enough to turn rock into vapor either failed to remove everything, or the moon received new water later. The right catastrophe has to be violent without being too perfect. The ages of lunar rocks create the next conflict. Many samples record major events around 4,350,000,000 years ago. Some zircon crystals are older and reach closer to the early history of the solar system. Francis Nimmo, Thorsten Klein, and Alessandro Morbidelli proposed that the younger age may not mark the original birth of the moon at all. The moon may have formed earlier and then suffered a second massive episode of melting. The engine would have been tides. When the moon was much closer, the pull of the Earth deformed its interior over and over. Rock flexed. Internal friction made heat. Large parts of the mantle may have melted again, resetting the clocks inside many minerals, while a few durable zircons kept an older record. We may have spent years dating the second fire instead of the first morning. That idea connects something you can see at the beach with something that happened inside the young moon. Tides may have reheated the satellite when it was close. The same tidal exchange still slows the rotation of the Earth and pushes the moon farther away today. The moon is not a sealed evidence locker. It melted and cooled. The Earth stretched it while impacts hammered the surface. Lava later flooded huge basins. The evidence spent billions of years inside the same building that kept catching fire. Raluca Rufu, Odetta Haranson, and Haggai Peretz removed another assumption. What if there was no single perfect Theia collision? The young Earth may have suffered a series of smaller impacts. Each one could throw out enough material to make a small moon. Those moonlets would move to new orbits. Some would catch one another, others would collide, and their debris could merge into larger bodies until one moon remained. For a while, the young Earth may have had several moons in the sky. It sounds like something made for a science fiction poster. In the model, it is just traffic. Jacob Kegereis and colleagues at Durham University and NASA Ames found almost the opposite possibility. With higher resolution simulations, a large moon-like object can appear within hours after the impact. Instead of slowly collecting debris, a nearly finished satellite can be thrown directly into a wide orbit. In some runs, the outer layers contain a large share of Earth material, while more Theia material remains deeper inside. That offers a possible reason the surface rocks sound so terrestrial. Imagine a freeway crash where the wreckage assembles itself into a second car before the tow truck arrives. Physics does not care whether the result looks reasonable to us. On the edge of scientific discussion sits an idea that makes Theia look conservative. Rob de Meyer and Wim van Westerenen proposed that a natural nuclear explosion deep inside the young Earth could have blasted mantle material into orbit. In that model, the Moon looks like the Earth because it came directly from the Earth. No Theia fingerprint needs to be hidden. The price is a natural nuclear event powerful enough to throw a moon-sized amount of material into space, with no accepted evidence that such an event occurred. It is a minority hypothesis. It matters here because it shows how stubborn the chemical problem is. If another planet refuses to show up clearly in the Moon, eventually somebody asks whether the Earth could have done the whole job itself. Even capture has returned in a newer form. Darren Williams and Michael Zuger studied a case in which the future Moon could have belonged to a pair of large bodies. A close pass by the Earth could break the pair apart. One object escapes carrying energy away. The other remains on a stretched orbit that tides gradually reshape. The mechanism can work in celestial mechanics. The chemical resemblance still stands in the doorway with its arms crossed. If Theia really hit the Earth, where is the rest of it? Its metal may have joined the core of our planet. After 4.5 billion years, an iron atom does not carry a luggage tag saying which planet owned it first. The rocky mantle of Theia might be easier to recognize. Earthquakes send waves through the planet. Deep under Africa and the Pacific Ocean are two continent-sized regions where those waves slow down in unusual ways. Qian Yuan and colleagues propose that these giant structures may contain dense remnants of the mantle of Theia that sank toward the bottom of the Earth mantle after the collision. If that interpretation is right, the missing planet is split between the sky and the ground. Part of its material may be in the Moon. A much larger amount may be resting almost 3,000 miles beneath your shoes. There are competing explanations. Those deep structures may contain ancient oceanic crust dragged downward by plate tectonics. They may also be leftovers from the earliest molten Earth. Seismic waves can show that something unusual is there. They cannot print a name on it. The deepest hole humans have ever drilled goes only a little more than 7 miles. Compared with the depth of those structures, we have not opened the planet. We scratched the paint. The Moon has its own half that remained almost equally inaccessible. The same tides that slow the Earth also slowed the rotation of the Moon until it became tidally locked. The Moon still spins. It simply turns once in the same time it takes to go around the Earth. That is why the same face keeps looking back at us. The far side is not permanently dark. Sunlight reaches it normally. We simply cannot see it directly from Earth. When the Soviet Luna 3 spacecraft photographed that hemisphere in 1959, it looked surprisingly different. The near side has huge, dark basalt plains. The far side has almost none. Its crust is thicker on average, and its terrain is rougher. One moon grew up like two different worlds. Until 2024, every lunar sample returned to Earth came from the side facing us. Apollo sampled it. Soviet Luna missions sampled it. Chang'e 5 sampled it. Scientists were comparing two rooms while owning dust from only one. Chang'e 6 finally returned almost 2 kilograms of material from the South Pole Aitken Basin on the far side. The samples include basalt, around 2,800,000,000 years old, and a rare fragment much older than that. Volcanism happened on the far side, but magma reached the surface far less often. A thicker crust may have acted like a heavy garage door holding the magma below. The enormous South Pole Aitken impact may also have changed the deep interior. If the Moon contains an imperfect mixture of Earth and Theia material, the two hemispheres may preserve different chapters of how that mixture cooled. There was another practical problem. From the surface of the far side, the Earth is blocked by the Moon itself. Chang'e 6 could not simply point an antenna home. China needed a relay satellite positioned where it could communicate with both sides. Commands went from Earth to the relay and then down to the lander. Data came back the same way. To pick up a bag of dirt from the hidden half of the Moon, humanity first had to put a messenger in the sky. The mission also carried a French instrument called DORN that measured radioactive gases such as radon near the surface. For this story, the nationality matters less than the fact. Even after we learned how to land on the far side and route radio around the Moon, we still do not know exactly how much of the material under those instruments came from the old Earth and how much came from Theia. Seismology should help, but there is a strange gap in the record. Apollo seismometers listened to the moon for years. Then the network was shut down in 1977. For almost half a century, we have been arguing about the inside of the moon, with much of our best direct listening data coming from equipment built before the personal computer became normal in American homes. NASA plans to change that with the Farside Seismic Suite. It is designed to listen directly from the hemisphere Apollo never sampled and collect new seismic data after a silence lasting decades. The old Apollo data also created the most famous argument for a hollow moon. When spent rocket stages were deliberately crashed into the surface, the moon kept vibrating for a surprisingly long time. The phrase that it rang like a bell became irresistible. The observation was real. The bell was a metaphor. Lunar rock is dry and heavily fractured. On the Earth, water and mineral processes help fill cracks and damp vibrations. On the moon, seismic waves can bounce through broken rock for much longer. Apollo data support a layered rocky body with a mantle and a small metallic core. They do not show a giant empty shell. The moon is also still changing. As its interior cools, the body contracts. Over hundreds of millions of years, it has become smaller by roughly 150 feet. The crust wrinkles, young thrust faults form, and shallow moonquakes can occur around them. It behaves like an old rocky world slowly tightening its belt. That did not stop the artificial moon idea. In 1970, Mikhail Vassin and Alexander Sherbakov proposed that the moon could be an ancient constructed object covered by a natural layer of rock. Later, Christopher Knight and Alan Butler built another argument around numerical coincidences, eclipses, the unusual size of the moon compared with the Earth, and the effects the moon has on our planet. Their versions are not accepted scientific models, but the facts that attract people to them are real. The moon is unusually large relative to a rocky planet like Earth. It strongly affects tides. At the right distance, it can almost perfectly cover the sun during a total eclipse. Almost is important. The orbit is not a perfect circle. Sometimes the moon is too far away and leaves a bright ring around the sun. It is also moving away from the Earth. Hundreds of millions of years from now, total solar eclipses will disappear because the moon will look too small. For standard celestial mechanics, we happen to live during a temporary geometric coincidence. For people who see design, that temporary window becomes part of the design. Apollo left behind a simpler object that is still working in a strange way. The astronauts placed arrays of small glass reflectors on the surface. They have no batteries. They have no computer. They are basically carefully arranged pieces of glass. Observatories on Earth still fire laser pulses at them. At Apache Point in New Mexico, scientists can send light toward the moon and detect the tiny fraction that comes back. More than half a century after Apollo, the hardware still answers. Those measurements show that the moon is currently moving away from us by about 1.5 inches each year. Young Earth creationist writers such as Jake Hebert and Jonathan Henry use that number in a straightforward argument. If the moon is moving away today, run the clock backward at the same rate. Eventually, the moon reaches the Earth far sooner than 4.5 billion years ago. The arithmetic is easy. The assumption is the problem. The recession rate has not stayed constant. It depends on the distance between the Earth and moon, but it also depends on oceans and coastlines. Different continental layouts dissipate tidal energy at different rates. An Earth with different seas does not push the moon outward the same way the modern Earth does. Fossil corals make the change easier to feel. John Wells studied tiny growth patterns preserved in ancient coral skeletons. Around 400 million years ago, a year contained roughly 400 days. The year itself was not longer. The days were shorter, around 22 hours. The Earth was spinning faster. The moon was closer. Not long after formation, some models give days only a few hours long, although the exact number depends heavily on the impact scenario. Tides slowly transferred rotational energy away from the Earth and into the orbit of the moon. The same mechanism connects an ancient magma ocean, a fossil coral, and the high tide you can watch today on an American beach. Every tide along the Atlantic coast is part of a machine that started running before the first true ocean on Earth had settled into place. That machine is still changing the future. The days are still getting longer, extremely slowly. The moon is still moving outward. Total eclipses will eventually end. Over extremely long times, the tidal relationship would continue pushing the Earth and moon toward a more synchronized state, although the future evolution of the sun will transform the system first. The moon also affects the orientation of the Earth axis. Jacques Lasker and colleagues showed that the moon helps keep changes in the tilt of the Earth within a more limited range than some moonless models produce. Other researchers, including Jack Lissauer, found less extreme outcomes for a world without a large moon. So the honest answer is not that the Earth would instantly become a climate disaster without the moon. The effect depends on distance and on the pull of the other planets. It also changes as the solar system itself evolves. And because the moon keeps moving away, its stabilizing influence is not frozen in time either. What about life? Strong ancient tides may have helped concentrate organic molecules in coastal pools. Repeated wet and dry cycles may have created useful environments for chemistry, and later for organisms learning to survive outside water. A more stable planetary tilt may also have made some climates less chaotic. None of that proves that complex life required the moon. We have only one Earth. Nature did not leave a control planet next door with the moon removed. That uncertainty is exactly why the cultural versions never disappeared. In Greek mythology, Selene was the daughter of Theia. In Theosophy, Helena Blavatsky described a lunar chain as an earlier stage in cosmic evolution. Rudolf Steiner treated the separation of the moon from an ancient Earth as a spiritually necessary event. David Icke later pushed the idea into a modern conspiracy framework in which the moon acts as a kind of relay affecting human perception. These are not testable geological models. Their status is cultural, spiritual, or conspiratorial, depending on the version. But they keep circling the same emotional center. The moon is not merely nearby. It came from something before us and still affects the world below. American folk culture adds smaller claims. Farmers have used lunar planting calendars. People blame a full moon for poor sleep or strange behavior. Christian Kajochin and his team reported modest sleep changes around the full moon, while other studies failed to reproduce a stable effect. A bright moon outside a bedroom window can obviously disturb sleep. A hidden lunar clock inside every human body has not been established. The moon already does enough real work without giving it extra jobs. It raises tides and has slowed the Earth. It changes the geometry of eclipses. It also participates in the long-term behavior of the Earth axis and changes the night environment for animals. That usefulness is one reason the artificial moon idea is emotionally durable. A much larger satellite could have created more destructive tides. A tiny one would have had much less effect on rotation and the Earth axis. The moon we have sits in a strangely effective middle ground. That does not prove design. It explains why people keep seeing it. In April 2026, humans returned to the moon in a way they had not since Apollo. Artemis II carried NASA astronauts Reed Wiseman, Victor Glover, Christina Cook, and Canadian astronaut Jeremy Hansen around the moon. It was the first crewed journey to the lunar neighborhood in more than half a century. America had already walked there 6 times. It had brought back hundreds of pounds of rock. It had left reflectors that still answer lasers from New Mexico. It had smelled the dust and listened to moonquakes. Houston even kept sealed evidence waiting for future scientists. And the birth scene is still not settled. The giant impact remains the strongest general framework because it connects the small metallic core, the ancient melting, the composition of lunar rocks, and the motion of the Earth-Moon system. But it is no longer one clean movie of a Mars-sized object hitting a finished Earth. Theia may have been a close chemical neighbor. The collision may have involved 2 nearly equal worlds. It may have produced a synestia. Several smaller impacts may have built moonlets, or one high-resolution impact may have launched a nearly finished moon within hours. Later tides may have melted large parts of the moon again and reset some of its clocks. Water survived, arrived later, or both. The far side followed a geological history that we have only recently begun to sample. A piece of Theia may even be sitting at the bottom of the Earth mantle right now. After the collision, there may no longer have been an old Earth on one side and Theia on the other. Their metals sank inward. Their rocky mantles melted and mixed. Some of that material became the modern Earth. Some of it ended up in orbit. That is why the Apollo rocks made the story harder instead of easier. They may not be asking us which planet made the moon. They may be asking whether, after the collision, there were still 2 planets left to tell apart.